So now we're going to talk about a quantity that we're going to be using a lot, and this quantity is called the center of mass. So the center of mass of an object is just a point. Is a point where you can balance an object. So for example, if this is my M1 and this is my M2, then notice that because M2 is bigger than M1, the center of the mass is more towards, so the position of the center of mass is more towards the larger mass. So the position of the center of mass simply tells me where I can rotate. So for example, if this is my center of mass here, if I apply a force in this direction here, then the system is going to rotate in the clockwise direction. And if this is my center of mass, and if I apply a force below the center of mass, this will rotate in the counterclockwise direction. Now, if a force is applied at exactly the same position as the center of mass, then the object is just going to move in a straight line without any rotation. So again, the center of mass is a very useful quantity. All right. So now we're going to derive an equation that is going to let us calculate the center of mass for very simple systems. So suppose that I have two masses, M1 and M2, and let's say that so these two masses are rearranged such that the position vector of M1 is x1 and the position vector of M2 is x2. It's x2. Then I can calculate the position vector of the center of mass using this equation right here. So the center of mass is just given by M1 x1 plus M2 x2 divided by M1 plus M2. So this is the equation that I'm going to use when I calculate the center of mass of two objects right here. So for example, if x1 was equal to 0 and x2 is equal to d, and let's say if M2 is twice the mass of M1, then the center of mass is just going to be at 2/3. So it's just going to be equal to 2/3 times d. All right. So generally, if you have not just two masses, but if you have more than two masses, so if you have n different masses together, then the center of mass of the system can be written by this equation right here. So in mathematics, we can rewrite this equation here as the sum over I of mixi divided by the sum over I of mi. So the sum over I of mi just gives me the total mass of the system. And so if you rearrange this equation, you can write it as 1 over the total mass times the sum over I of mixi. So we use this equation if you have more than two masses in your system that you want to calculate the center of mass. Now, generally, if I have a system that is not just, if the masses are not just placed on the x-axis, but if I have a system where some of the masses are also placed on the xy plane, then it means that the center of mass is going to be a vector. So I can calculate the x center of mass using this equation. I can calculate the y center of mass using this equation, and the z center of mass using this equation. So again, if I'm not just looking at masses that are on the x-axis, but if the masses are rearranged in such a way that some of the masses are placed on the y-axis and on the z-axis, then it means that the center of mass is going to be a vector quantity that will have three components. So the x component is given by this equation, the y component is given by this equation, and the z component is given by this equation right here. So generally, again, as I was saying, so the center of mass in this case is just, so it's going to be written as a vector. It's x center of mass I plus y center of mass g plus z center of mass in the k direction. So we can write it in that form. All right. So now we're going to extend the definition of the center of mass to a distribution. So this is a distribution here. So you have a mass, whereas these are not like discrete masses, but this is just a distribution of masses. axis here. So, so generally we said that we can write the x center of mass by using this equation here. So we can write it as 1 over m, the sum over I of xi, delta mi. And then generally, if we keep, so again, so the basic idea is that you want to take your system. So this is a continuous system. The masses are not discrete, but we can use calculus to estimate what the center of mass is using this equation right here. So in the limit in which delta mi becomes very small, this equation becomes an integral that can be written in this form. So I can calculate my x center of mass as 1 over m, the integral of x dx. And again, if I want to calculate what the y center of mass is, I do the same calculation here. It's just going to be 1 over the total mass of the system, the integral of y dm. And z center of mass is going to be 1 over total mass, the integral of z dm. So again, if I want to write this as a vector quantity, I can just write it in this form right here. All right. So the center of mass is a quantity that is, so there is a quantity called the center of gravity that is kind of similar to the center of mass, but it is a little bit different. So for example, if you look at a range, so if you look at a range here, so this is hung freely from point A and then from point C. Then the intersection of the two lines AB and CD locates the center of gravity. So again, the center of gravity is just the point. So for example, if I were to calculate the force of gravity, then I would say that the force of gravity is acting at this point. All right. So now I'll let this, so this is quick quiz number 9.7. I'm going to let you guys look at this example right here. But again, you can see that this is an example. This is a baseball bat. You can see that the mass is not uniform. It's not uniformly distributed because you have more mass on the right side compared to the left side. So for example, if I were to calculate the center of mass of this baseball bat, you're going to notice that the center of mass is going to be located more towards the right because it's not a uniform distribution of the mass. All right. So now let's look at one example here. So in this example, this is example number 9.10. We want to calculate the center of mass of 3 particles. So suppose that we have a system that consists of 3 particles located as shown in the figure, and want to find the center of mass of the system. And then so we have 3 particles, M1, M2, and M3. So notice that M1 and M2 are located in the x-axis, while M3 is placed on the y-axis. And it tells me that M1 is equals to M2 is equals to 1.0 kilograms, and M3 is equals to 2.0 kilograms. So I want to locate where the position of the center of mass is going to be. So I can use my equations here. So I can calculate my x center of mass as M1 x1 plus M2 x2 plus M3 x3 divided by M1 plus M2 plus M3. If I do that, I get my x center of mass as 0.7 meters. Then if you calculate your y center of mass, it's just given by M1 y1 plus M2 y2 plus M3 y3 divided by M1 plus M2 plus M3. So again, if you plug that into the equation, you get your y center of mass is equals to 1.0 meters. So again, this is an example where we have 3 particles. So the x center of mass is 0.75, the y center of mass is 1.0. And so we can write the position vector of the center of mass using this equation right here. It's just 0.75i plus 1.0j meters. All right. So now let's look at this final example here. So this is example number 9.11. So we're going to calculate the center of mass of a rod. So notice that because I have a rod, so the mass is uniformly distributed here. So if I want to calculate the center of mass, then we need to use calculus to do that. So when we set up this problem here, I can write my, so I can say let dn, so let dn be equals to lambda times dx. So again, lambda is just the mass per unit length that I have in my system, and the distance from this point to this point is x, and let the distance from here to here be dx. So it means that I can write my x center of mass as 1 over m, the integral of x dm, but I know that my dm is given by lambda times dx. And so if you do this integral here, you just get lambda over m, and then you have x squared over 2. And so if you do that integral, you get lambda L squared over 2m. And then we're going to go back. We know that this lambda is just the mass per unit length. So if you substitute that by mass per unit length and you solve that equation, you get 1 over 2 times L. So we notice that this is a uniform mass distribution. It tells me that the center of mass is going to be exactly midway, halfway, right at the middle, right at the center, right here at the point L over 2, because this is a very uniform distribution of mass. All right. Now let's suppose that we have a rod that is non-uniform, such that its mass per unit length is going to vary linearly with x according to this equation right here. And then find the x coordinate of the center of mass as a fraction of L. So now we have a mass such that the mass per unit length is not uniform, but it varies. So what this tells me that is that I have more mass on the right side of the rod compared to the left side of the rod. So the way we solve this is that first of all you write your dm as your lambda times dx, where your lambda is given by alpha times x. And then if you calculate your x center of mass, you just plug everything into this integral here. You get alpha over m, the integral from 0 to L x squared dx. This will give you alpha L to the power 3 over 3m. Now the total mass is given by the integral of dm, which is the integral from 0 to L of lambda dx, which is equal to the integral from 0 to L of alpha x dx. So this will just give me alpha L squared over 2. So it means that from this equation I can find my alpha. So I can find my alpha. So in this case here, if I solve for alpha here and plug it into that equation here, then I get my x center of mass, which is just at the point 2/3